My very good afternoon to all my fellow delegates present here in this session, uh, and also my wishes to the delegates who are joining remotely over this session. This session today is our combined presentation together with Charlie, who is on behalf of Sulzer GTC. With that, I think I would request him to join me as well as we continue through the session. So today session is to actually introduce the alliance which has been signed by Axens and Sulzer GTC. And in few words, this alliance is about bringing to the market a technology which actually lets you conserve the RON of your FCC gasoline, and also to provide flexibility for the operation of the refineries such that you can produce petrochemical products. So this is about Axens. We all know, and the Axens as a company, we are the technology licensors and Sulzer GTC. So with this, I shall go into an introduction for Axens Prime G technology, and over the session, I would let Charlie take over for presenting his part. So Axens Prime G technology actually consists of three major stages. The first one is a selective hydrogenation stage, whose main function is to actually selectively hydrogenate the diolefins and also to have sulfur shift from lighter mercaptans to heavier mercaptans. So the catalyst employed is Axens selective hydrogenation catalyst. The second stage is a naphtha splitter column, as you see. The function of the naphtha splitter is to lift the lighter olefins to actually top, which is called as the light cracked naphtha. And the aim is to actually blend this light cracked naphtha directly into the gasoline pool, because it is very rich in RON. You cannot actually hydrotreat that and lose the RON. The heavy cracked naphtha, which is concentrated in the heavier sulfurs, is actually going to the HDS unit, and the HDS is the third stage where we actually have a very selective HDS such that no olefins are saturated, and we are able to conserve the RON of this stream. So this stream, after stabilization, meets the BS6 specifications, and then it's blended with the gasoline pool of the refinery. Moving forward, I would let Charlie join me here and present the extraction technology.
Thank you, Anuj. So Anuj gave you the general idea about what the Prime G process look like. So I'm going to show you what the general idea of the GDBTX Plus process look like. So GDBTX Plus, as you can see right here, is a extractive distillation system that consists only two major columns. The first column is called EDC column, the second column is called SRC column. It's a pure extraction technology with there's no chemical reaction happening inside this process. So what we do is we take the FCC gasoline that contain different components, as you can see, PONA on the left and S represents sulfur. So with the PONA and sulfur in the feed, the aromatics and the sulfur are being extracted by the solvent to become the extract, while all the non-aromatics, the PON, are being rejected to become the refined product. This is a process specifically designed for the FCC naphtha. And I'm going to turn it back to Anuj to tell you when these two processes combine, what we can do for the FCC gasoline.
Thank you, Charlie. So now getting into the combined offer of Axens Prime G and GTBTX Plus, what we need to have a look upon is the market trends. So if you look at the screen on the top left, what you see is the demand of the coming years compared to 2020. And we all know, which we have been discussing, that the refineries would be shifting to very integrated mode with petrochemicals. We see that the gasoline demand is going down. We all agree that the lowering demand will actually hit the revenue of the refiners. What we see on the top right is the gasoline price in the market, and we know it has been very volatile over the years, and it's also on a downward trend. Now, low demand coupled with the low price always obviously will hit the margins of the refinery. So what do we have in hand? There is a third cost center, what we call as the octane barrel. Now, what is octane barrel? First of all, what you see here is the distribution of the octane barrel over different regions. So this octane barrel changes from an Asian region to the US Gulf Coast, and there are different statistics about that. Now, octane barrel, in a very basic sense, is the incremental cost a refiner pays per barrel of the gasoline to raise the octane by 1 compared to the average what you are getting in the refinery. So you would draw a parallel that if you are treating an FCC naphtha and you are losing RON, then actually you are getting hit on the octane barrel to a large extent. So supporting with an example for a 50,000 barrel per stream day FCC treater. Now if you talk of maybe the 40% of that is coming out as naphtha. So if it is operating, if this FCC post-treatment is taking place at an octane loss of around 3, octane barrel of $1.5 will actually translate to a loss of around $37 million in a year. So that's the cost what we are talking about. We all can do the mathematics compared to the catalyst cost, compared to the investments, and we could see that what is happening, and frankly, this is the innovative integrated approach which Axens and Sulzer GTC bringing together to think about that. Now, Axens Prime G has a number of configurations, and these configuration of the Prime G unit actually depends on the level of the RON a refiner is looking for, what is the feedstock property, what is the budget of the refiner, and as well as what is the available plot space. So these various configurations which you see here have been licensed by Axens, and all of these have been running for some refinery or the other. Now, with the integrated approach, with the combined offer of the GT-BTX extraction process, the HDS step, what we were talking about in the previous slides, that could be improved further. And this actually will translate into a better RON retention compared to a standalone prime. So getting into a little bit of chemistry, what you would see on the left-hand side of the slide is a typical composition of FCC naphtha. So you are seeing there are greens, the bars, those are telling you those are the olefins. Olefins are very high in RON, we need to conserve them. Sulfurs also are distributed among the same cut points. So we need to devise an approach to treat them. So that is what Prime G is all about. Now, in a combined offer with GT-BTX Plus, the Chou reactor, selective hydrogenation, and the HDS actually retain their functions what they were doing in the original Prime G. The naphtha splitter is modified, so you would see that there is a MCN. Now, MCN is an intermediate stream, and it's also called as hard cut. Refiners would be knowing. So this MCN is directed to the GT-BTX Plus unit. From the GT-BTX Plus, we get, first of all, a raffinate, which is again highly rich in olefins. So we concentrate the olefins, which you see in green, to this MCN cut, again conserving the RON, and the unit is designed that you blend this now directly into the gasoline pool. So we are conserving the RON here. Then there is an extract. The extract is something which is very rich in sulfur and also carries a lot of aromatics. Now, depending on the potential of the feed, right, these aromatics is something what Charlie will cover, and how do we take that in the later part. So, schematic that all the sulfurs is then sent to the HDS, and as you would see again on the left that the cut point 150 to 190 sulfurs would be again concentrated to heavy cracked naphtha. Now we call it HHCN. And then once these HHCN, which is low in olefins, we treat this in the HDS. Again, the selective catalyst by Axens come in play, and then with a very little saturation of the olefins, we are able to get the HDS. This is stabilized, and then the product is blended with the gasoline pool. One very important thing to note here is that the HDS throughput has gone down here, right? Because we are now treating less stream as compared to the original configuration of the Prime G. The hydrogen consumption has gone down because you are not actually saturating those olefins which you were doing earlier. So this would come as a cost saving, and when we discuss about the commercial parts later in the case study, I would see how that, we can see how that affects the profitability. So now this is something which we can relate to the extent of the possibilities with the combined offer of the Prime G and GTBTX Plus. What you see here is a graph which shows the delta RON relationship with the percent HDS. If you do a desulfurization step on a FCC naphtha, you are bound to saturate the olefins. There is a RON loss that would happen. So this is the graph which shows that. And for a very basic one-stage scheme of Axens, which you see in orange, this combined with a finishing reactor, there is an exponential relationship between the RON loss and HDS. So the deeper you go in HDS, the higher RON loss you have. Now, one improvisation on this can be the green part which you see. This is a two-stage Prime G process, and we lower down the RON loss for the same level of HDS as you are seeing. Here comes the combined offer with the GTBTX Plus. The relationship can be gone to linear, and the curve becomes very flat. And then we are talking about RON losses of even less than 1. And it would not be false to say that the Prime G and GTBTX Plus solution combined can offer you a RON loss much better than the other commercially available technologies over the market. So I'm sure, moving on, that with this information which I have provided, everybody would be interested is that what about the commercial aspects, right? What happens commercially? So let's go into a case study which has been developed to compare the operational costs before the installation of GTBTX Plus and after that. What you see here is a basic scheme, one stage with a finishing reactor by Axens. Now, the table on the right is very simple, but then there are two tables you will note. The first table actually gives you the operational cost associated directly with the utilities like electric power, fuel gas, steam and cooling water and hydrogen. So this, for an average sized FCC naphtha hydrotreater, comes at around $12.85 million. Now, if you remember, we talked about the octane barrel. The octane barrel is related to your octane loss, and it's the incremental value a refiner pays for getting a better RON by 1 of the average what he is producing. And then that is very important considering the premium gasoline range like 92 to 95, 98 RON as well. So octane barrel is also a high cost center, and the loss, let's say if you are operating on a RON loss of 2, this octane barrel brings in additional operational loss of around $18 million. And then combined basis, we understand that the operational utilities going in are roughly to the tune of $32 million. And next, we compare it with the combined GTBTX Plus solution. So here you would see that an MCN splitter has been added an extra. So MCN splitter is added to actually control the properties of that intermediate stream, and you will see that we have been able to raise the FBP almost to around 150 degrees Celsius. So the more you, this is the flexibility we get added with an MCN splitter. Now if we compare these utilities, again it is very simple that the utility consumption goes a little higher because we are adding a splitter and we are taking some more material out. So this combined with an octane barrel, now the loss has been reduced to around 0.4. So combined basis, this brings down our operational cost to around $20 million. Maths is very simple. You get a payback of almost $12 million in a year. And then I think we can always correlate it with the investment a refiner would be doing to install a GTBTX Plus. And I think that will bring out the payback for a refiner. So summarizing the gasoline mode, this enables you to have the lowest octane loss, as I said, compared to other commercially available technologies. This, both for a revamped unit or a grassroots unit, lets you have a lower capex, lower utility consumption, and even the optimization of the catalyst volume, which you put in a Prime G unit. Overall, with the payback, with the saving of around $10 million in a year, the payback for the average unit comes to be less than 2 years. With this, I think I will hand over to Charlie, who will go into the details on the petrochemical possibilities, right?
Thank you, Anuj. So, as Anuj said at the beginning, our combined offer not only help the existing refinery FCC unit to have the ultra low sulfur FCC gasoline with almost no octane loss, it actually have another mode to operate, a petrochemical mode. So to save the octane is a gasoline mode, but the same solution has a petrochemical mode to operate that can give the refinery additional petrochemical product. And why is this important? Because as you know, while right now the gasoline may be a pretty good product, the price is high, but all the study shows globally the gasoline market will eventually drop and will keep dropping in the long term. So it is important to know this trend to plan your refinery's future. So the gasoline demand will continue to drop, while the study shows that the petrochemical product demand is still continuously grow at a healthy pace. So we can see a lot of new refineries being built. They are already start at the beginning to plan, to design the whole refinery to maximize the crude to petrochemical or the crude to chemical. But that also posed the challenge to existing refinery for how are they going to do with their refinery that designed originally for making the fuel. When the fuel is no longer a favorite product, how can they utilize the existing facilities to convert the gasoline to petrochemical? And our combined solution, the Prime G Plus and the GDBTX Plus, will also provide this solution to the industry. So how do we do that? It's actually very simple. This configuration you see right here is the same configuration that Anuj shows just a few minutes ago for the combined solution to minimize the octane loss. When you operate at the petrochemical mode, you will have exactly the same configuration, the same MCN cut, and the same GDBTX Plus unit with the same raffinate and the same extract. The only difference when it operates at the petrochemical mode is the extract will be diverted to a separate HDS. And this HDS will operate at a little higher severity to reduce the sulfur to be less than 1 ppm. Once the sulfur is less than 1 ppm, then right away you will get the BTX and even the C9 aromatics as a petrochemical product. The reason is the extraction is very efficient, so that the extract itself is already a pure aromatics. The only impurity in that extract is the sulfur. So once we use the HDS to remove the sulfur, then right away you get the aromatic product. More than that, when you look at the raffinate from the GDBTX Plus, the raffinate has no aromatics, and it's very rich in olefins. The olefin content right here can be as high as half of the stream. So this actually is a perfect stream for the refinery to recycle to the FCC or RFCC or high severity FCC, and that will crack the olefins in this stream into additional propylene. So if you would like maximizing the propylene in your refinery, then this will be a good additional feed for you to send back to the FCC unit. And just to make show some numbers so you can get a better picture, for a typical 50,000 barrels per day FCC, let's say 30% BTX and C9 aromatics in the full range FCC gasoline. By taking those BTX and C9 aromatics out, you can expect to have a 300 KTA of a BTX C9 aromatics product. That is already a world scale aromatics plant. And also when you recycle the raffinate back to the FCC, it is also can be expected to have additional 2 to 6% of the additional propylene, and that is a huge propylene addition to the refinery. If some refinery, they do not want to have additional propylene, they only want to focus on the additional BTX. We also have another option. There's a technology called aromatization that can take the olefinic stream and convert the olefinic stream into additional aromatics. So it can take the raffinate as well as the LCN to react and become more BTX. For some refineries, they are sending their existing FCC naphtha into their straight run naphtha hydrotreater and followed by the CCR to make the raffinate. While we see this is not the perfect configuration, but if your refinery is doing this configuration, then GDBTX Plus can also help you to improve the efficiency. Because when you send the FCC gasoline to the naphtha hydrotreater and the reformer, the aromatic content inside the FCC gasoline is taking a free ride. The aromatic content is doing nothing at all in the naphtha hydrotreater and in the reformer. So when the extraction unit GDBTX Plus taking the aromatics out, before you send to the naphtha hydrotreater and the reformer, you can best utilize this naphtha hydrotreater and reformer to fully convert the non-aromatics into additional aromatics with the minimum energy. So let's make some case study to show you some figures. This is a case that contains processing 25,000 barrels per day or about 125 tons per hour of FCC gasoline. This is a typical prime G configuration and the final product is the gasoline. If you are operating the petrochemical mode and using the GDBTX Plus, then you can expect to have about 2.3 tons per hour of benzene, about 8 tons per hour of toluene, and about 15.5 tons of mixed xylene can be the BTX product from this stream. Then we estimate the total investment of the additional unit. We calculate the BTX price minus the cost, the raw material cost, which we consider the BTX octane value. Because if you don't take it out, then it's contribute to the octane in the gasoline. So we use the BTX value minus the BTX octane value. Then we can calculate the gross profit. And then we also know the operating cost of this additional unit. Then all in all, we calculate the additional profit, and with the additional net profit, we can calculate the project return. So the project return in this case is 62%, or 1.6 year. It's a very significant high return project, and we have not even considered the additional benefit of the existing prime G catalyst life can be extended simply because the throughput to the existing prime G unit has been reduced to roughly 1/3 or even a quarter. And there is additional benefit of if you choose to recycle the raffinate back to FCC, you will get additional propylene. So just a summary for the petrochemical mode on this combined offer. So first, it gives the refinery choice to convert the gasoline to petrochemical, which is BTX and extra propylene. It can also reduce the hydrogen consumption, the same as in the gasoline mode. The additional HDS that I mentioned that to process the extract to reduce the sulfur to less than 1 ppm, that can actually be reused, the same reactor that's in the two-stage prime GHDS, so that you don't need to build a new reactor for that. It's a very high return project. Typically, the return of the investment is less than 2 years. It also reduced the CO2 footprint because the refinery will be producing the petrochemical instead of the combustible fuel product, and it's a commercial proven technology. So just a recap of both gasoline mode and the petrochemical mode of this combined offer. While I think it's very clear right now, this combined offer will, at a gasoline mode, that can give the refinery highest quality gasoline with almost no octane loss. And whatever your octane loss right now in your FCC FCC gasoline product, with the dropping GDBTX plus, it will become nearly zero. And the same unit, you can operate a petrochemical mode that can convert the gasoline to petrochemical. And more unique about this combined offer is the flexibility. So you just need to put in one-time investment for this configuration, and you are free to switch between the gasoline mode and the petrochemical mode at any moment. So you put the investment right now for the gasoline to maximize the gasoline profitability, and you do not need additional investment when 10 years later the gasoline market change and you have to produce petrochemical. You do not need a new investment, just simply switch the next day. You can start to convert the gasoline to petrochemical. This flexibility will be invaluable to the current refinery to stay on the top. With that, I conclude this combined presentation by Axens and Sulzer GDC. We'll be happy